Great. Okay. So I'm Tom. There's a slight chance you know me as that Tarsier guy from the internet. I usually start with a picture of my Twitter account and then explain what's there. So it's a good one today because my most viral tweet ever, unfortunately, somebody else's image, not my joke. But beautiful typesetting with latex. Give to Medicine Sans Frontières if you can, is my injunction there. So there's 3 links. I'll share the slides at the end. You might be tempted to give to the NHS, but in reality, our NHS should be funded by taxation. It's not a charity. So I suggest you send your money to MSF because they go places that other people are not going. And if you wonder why the NHS isn't a charity, and if you're thinking there's no magic money tree we can shake to pay for essential services as part of a industrialized nation, then you might want to start looking into the tax justice network. So that ends the intro. So I'm going to talk about block devices and layering of different block devices. So we have to understand this in order to understand everything else. So this is papers we love on, I think, about 7 different papers I love as offshoots or precursors to the one that was announced. So I hope this is interesting for you. So yeah, in order to understand all this stuff, first we should talk about block devices though. So we've all probably experienced them. You get a hard drive and you format it with some file system. You get a USB stick, you format it with some file system. People have typically understand that. So you have this interface that says that there's a number of blocks. You can take a particular block and read or write to it. And that's a very simplistic interface. So we then layer atop it another interface called a file system, which is a namespace that says create these folders, create these files, and those files ultimately become data inside the blocks on your block device. So it's a useful abstraction. And we're going to talk about ways of combining those block devices in ways that are performance enhancing and redundant. So we are going to talk about RAID systems, which means redundant array of inexpensive disks. So there's your sort of picture of a block device, sequence of blocks labeled A1, 2, 3. And we're saying we can go and I can read A2 or I can rewrite A2. And something that consumes this might be, for instance, a file system, or maybe a database directly consumes a block device. I'm guessing that lots of you know this, but so I'll step through it quite quickly. You've got sort of logically, sorry for getting ahead of myself on the slides there. You've got kind of logically a couple of things you could do. So let's say you've got 2 block devices, 2 disks, and you want to combine them. You could say, well, you could just do a simple concatenation of them. I'm afraid in talks I often rely on waving my hands, so I'm going to try and do best at what I see in the video is like what I want you to see. So if you can minimize it and make sure you can see me, that's good. So running the 2 disks end to end. So the first load of blocks are on this disk, the last load of blocks are on this disk, and you've got one combined disk that is the both of them. Now the disadvantage there, if you're often at the beginning of the disk, you're only hitting one, or the beginning of the combined block device rather, you're only hitting one of your disks. So performance enhancement people do is RAID 0, where you alternate blocks between the disks. So if you're reading a sequence of blocks in your block device, you'll actually be hitting alternate disks, which gives the disk a chance to fetch the data, etc. Because disks, of course, have like of course, for a long time, had like a platter that's spinning and then an arm that's moving to read the data. So RAID 0 would be performance enhancing in the case of as we're writing to 2 different disks. As we're reading from 2 different disks. But the problem is, if either fails, our block device no longer exists. So 2 disks combined into 1 block device, and we've made our performance better, but our reliability worse. Another way of combining 2 disks is to say, well, every time we write something, we write it to both disks. So that potentially takes you longer. You're as fast as the slowest of them. But when you read, you can read from either. And if you lose one, you can just read from the other. So we've gained availability. We've got slightly more expensive writes because we have to wait for both to complete. And we've got an option of reading from either. If we wanted to be careful, we could read from both and compare them, but we don't have a way of knowing which is right and which is wrong. So it's not super useful for us. So that's what we're going to talk about, is layers and layers of these things, because that's what Erasure coding, which is where we're getting to, is about. It's a way of taking a block of data or a sequence of data and carving it up in such a way and distributing it in such a way that we can efficiently recover the data that we want. But I'll get to that. That's about the 7th paper now. So so far so good. RAID 4 is a way of combining the 4 disks in this example and calculating A1, A2, A3 are just bits of data. AP is the parity of that data. We'll talk about what that means in a second. B1, B2, B3, and then the parity of that B block. So we're saying our data is on 3 disks, and this so-called parity information is on the 4th disk. Parity, by the way, the odd or evenness is the answer to the pre-question. You can actually save 99 of the people on the benign planet whose name I temporarily forgotten. So we're going to write this parity information, and from that parity information, we can recover any of the data from the other drives that's missing. And the problem being, though, that if you're writing data and then writing parity, you've got all of the parity information on 1 disk in this case for RAID 4. I've ignored RAID 2, and RAID 3 because they do parity or redundancy at the level of bytes rather than blocks. So, but that was mostly ignored after a while. So we're doing parity at the level of blocks, which are like useful units of data, and that might be like 1 meg, or it might be a smaller unit, whatever, but it's some fixed size amount of data. So yeah, and you can see here the efficiency would be, we've used 1 of our 4 disks, so the efficiency would be like 75% utilizable of our 4 disks. RAID 5 just distributes the parity, so it turns out it's a nice performance enhancement to spread out those parity blocks, but it's the same idea as RAID 4 in principle. For every 3 blocks of data you write, you have to write a parity. 3 blocks of data have to write a parity. That's exactly where we're going with Erasure codes in a moment. So RAID 5 looks like this, very, very common. So how do you rebuild RAID 5? So it's parity. It's an XOR calculation. Parity means the odd or evenness of it. So here, if I've got a bunch of data there with something missing, and RAID 5, this rightmost column represents the parity or the XOR calculation, we can rebuild it. So you can all unmute yourselves and shout these out. What's this one have to be if the XOR of them all is 1?
1
is true. Yes. I don't know who said it. I'm afraid we did this with Renzo before. When I actually, you've shrunk to a tiny screen. I can only see 4 of you, but yeah, you're exactly right. The 1 and the 1 that exists would cancel one another out, and we're saying in order for there to be an odd number of 1s, that missing 1 has to be 1, right? Here, that has to be 0. That would have to be 1. That would have to be 0. Shout if I make a mistake, please. That would have to be 0, I think. That would have to be 0, I think. That would have to be 0, I think. And that would have to be 1, I think. So if I didn't make any mistakes there, you should be able to look for a particular line and say, well, if there's, for the bottommost one, if that's a 1, if there's an odd number of 1s there, if the XOR of all those other things is 1, then that has to be 1. So we can recover from RAID 5 by XOR. XOR is really nice in that it's actually self-inverse. So if you take the parity and XOR everything, whatever, sorry, if you take whatever's left and you're missing some data and you XOR it all, what is left, what is the answer, sorry, is what's missing. Sorry, that wasn't very clear. RAID 6 has a second parity, or has a second block of redundant data that will allow you to recover from 2 failures. So it's very common to refer to these extra blocks as parity, even though they're not all calculated with XOR. So it's a somewhat confusing language, but this is a second block distributed amongst our disks that allows us to survive 2 failures rather than 1. And can we use XOR twice? You might be thinking XOR is a good trick. It solved the logic puzzle from earlier. We've just shown we can recover data if we lose it. And the answer is we can't. So the explanation is if the XOR of that data is 1, then that means either the first one's 1 and the second one's 0, or the first one's 0 and the second one's 1. We've got somehow like saving the same information twice, saving the parity twice doesn't help us recover, because you're in the situation where there's 4 possibilities if you've lost 2 bits of data, and you can only limit it to half of them. You either know they're both the same or you know they're both different. You don't have a good way of saying which of the 4 possibilities it is. Does that make sense? Does anyone want to holler at this point and ask any questions? I'm afraid it's mildly disconcerting still, because I can only see Renzo's face. So if nobody's hollering, I'm going to continue. So any form of RAID that can use 2 parity blocks and a number of data blocks counts as RAID 6. So RAID 6 doesn't have a definition beyond that. And it says that several methods have been used. Dual check data computation, so Parity and ReedSolomon, which we're going to talk about in a moment. That's very common. Orthogonal dual parity data, so instead of going across the disks, go diagonally, or some other combination. So still use XOR, but not on the same disks. And that then is somehow enough information to recover what you want. But that also leads to more reads. So one of the things we're going to talk about today is, in the recovery, what do we have to look at in order to do the recovery? So for RAID 6 or RAID 5, in the absence of one disk, you have to look at all the other disks and sometimes the other parity. So in the case of RAID 5, if you lose a disk, you look at the parity in all the disks. If you lose a parity, you can recalculate it by looking at all the disks. For RAID 6, there's a few options. If you lose 2, they're either both parity or one's parity or none is parity. Sorry, 3 options. And in any case, you have to look at all of the other disks in order to calculate it. In the case where we're spreading the data over multiple machines, that's multiple fetches to some other machine, which, as we know, is slower than things that are on your machine, usually, or often, let's say. Other machines' memory are potentially faster than your disks, though, we should remember. Okay, so how RAID 6 is implemented in the Linux kernel uses the ReedSolomon encoding option, which is the most common. Last time I gave a talk at Papers We Love, I think I did, well, at least attempt an exposition of Galois algebra. I think it's going to suffice now. I'm going to be a bit flippant with mathematics in this talk, which my degree was in mathematics, so this isn't an unusual situation for me. So we're going to say, this paper is very good, by the way. It starts with a quick summary of Galois algebra. It doesn't, I think it's pedagogically unsound in the sense that it doesn't say that most of the things he introduces are just the definition of a field. Like, in order to, like 1, 2, 3, 4 there are just parts of the definition of what it means to be a field. So a field is an algebraic structure that behaves like numbers in some sense. So you've got an addition, you've got a subtraction, you've got a multiplication, you've got a division, you've got a 0 element, you've got a 1 element. So it's an algebraic structure that's like rich enough to permit an arithmetic, to talk a little bit loosely. But what they're saying is, here's a second equation you can use. If P, the parity equation, is just the XOR of all the data, addition in that field is XOR. So you're fine to just add the elements together. Q, you're doing some other equation, whatever that means in the Galois field. So that's that's the paper. Cheers, Mark. So if don't read it now though, because I'm about to punt and move on. So yeah, Q is referred to as a ReedSolomon code, so it's a ReedSolomon code. They're not unique, but ReedSolomon codes have a property that you can have 6 data blocks and say 4 parity blocks, and you've spent 10 for 6 lots of data, and you can have 4 of them fail, any 4 of the 10, say. Most common deployment is RAID 6, which is some number of data blocks and 2 parity blocks. And the reason being, and this paper does it quite nicely, is that solving arbitrary ReedSolomon equations is increasingly hard. And to solve the general one is quite difficult. And if you're doing it on one machine and you want it to be fast, you need optimizations. So there's the actual solution. So if there's two equations you can use, here's the solution of the two equations, and here's how to make it fast on modern CPUs as of 10 years ago. Interestingly for me, and I'm not going to feign any deep knowledge here because I'm not a low-level machine instruction type guy. In fact, the C in this is inscrutable to me, so I'm not going to feign any great knowledge here. But very interesting is that actually a lookup table is slower than mapping everything to XORs because of SIMD instructions, because of automatic parallelization of CPU architecture. And this paper is a relatively old paper, so yeah, not feigning any deep knowledge, but I think lots of our intuitions about what will go fast are kind of disproven by the fact that processors will do out of order and preemptive executions, etc. So that's the kind of RAID 6 case. So this paper points to another paper which says, here's a great tutorial on ReedSolomon Code. It's more broadly, goes a little bit more in depth into what the Galois fields are, etc. But really, really interesting is this is from 1996, and he's got the flag in front of it now. Important, the dispersal matrix I gave you is not correct. But the paper otherwise makes sense, which is interesting, right? It's like, makes sense, but the matrix I told you to use isn't correct. So that idea is going to come back throughout this presentation. Is like, a lot of these things are, we chose a smart matrix. And the reason that's important is this is the wrong one. The correct dispersal matrix is this one. So saying, here is a good matrix. And a lot of these papers we're going to be reading are essentially Appendix N. Here is a good matrix. Like, use this matrix, it will work. Or use this algorithm to generate the matrix, which will make it work. So whereas the last talk, which I don't think a recording exists of, or whereas a whole interesting field you might want to study is, well, what does that mean? Like, what does arithmetic in this Galois field mean? Well, I'm going to punt that, not because I don't think it's worthwhile, but because there's enough interesting stuff later on in these papers to kind of entertain us for this evening. So I'm going to pause here. Oh, sorry. So here we go is an example of a Galois field. So the binary element, binary representation, and also this polynomial element. So it's the Galois field we use is actually, if you like, it's a weird arithmetic on bytes. So plus is XOR, multiply is the equivalent to some polynomial multiplication. So you may not remember that you can multiply and divide polynomials, but you can, and that also is a field. It also has a whole arithmetic under certain conditions. So the reason matrices are so important is we're trying to solve equations, right? We're trying to solve, we've got multiple equations. So in the RAID 6 case, it's two equations with two unknowns. And you may remember from secondary school maths, two equations with two unknowns you can solve unless the equations are somehow related, unless the collinear it usually is, if the linear equations. So if one's a multiple of the other one, it's redundant information. So you can't actually solve it. That's related to matrices. This is a thing called Gaussian elimination that says the system of linear equations is the same as doing operations on a matrix. And if the matrix is invertible, then the system of linear equations is solvable. And solvable means, in this case, you get your data back. So that's why here is a good matrix is a really good property to have, or a really good thing to show somebody. It's like, use this matrix or generate this matrix. And then you can solve your equations. When solving the equations, in this case, means getting your data back. So I'm going to pause because I'm just staring at Renzo's face, excuse me. Does anybody have any questions at this point? Or comments even? I feel very lonely talking into the void.
Hey, Andrey, do you want to talk about that case where you lost the parity? I know it was a little bit ago, but
yeah, that's an interesting one. With I think first of all, when we increase the number of parity blocks, do we expect to also increase the redundancy and increase our, well, how many blocks we can lose?
Yeah, that's very common. So it's a great question, and it highlights something I meant to mention. So let's talk about recovery in the case of, oh no, actually, you've anticipated something I'm going to talk about in a moment. So if you'll permit me, I'll go forward rather than backwards. I misremembered the order of my slides. So we can actually layer the parity information. So in the case of RAID 5 and RAID 6, you have some number of data blocks and you have some number of parity blocks. So typically it would be a number less than about 8, typically in a single machine RAID system. And the reason is if you're writing 8 lots of data. If you're writing whole blocks, then you can write data, parity, and you're golden. In the case where you update something within a block, there's a write penalty for RAID that says, well, you have to write in the general. Well, if you weren't smart about it, you would have to read all the old data and recalculate the parity. But because it's XOR, you can say, well, the new data for this block changes the parity. So you've got the old data, the new data, and you can generate the new parity then. So you pay a write penalty with RAID 5. The problem is in the recovery path. When you've lost one disk, you're doing that calculation to read every block, and that will slow you down. The problem is as well, when you put a new disk in and you start to recover, in order to recover into that disk, you're reading from every other disk. And that's exactly when the other disk fails, because that's not like your normal use case. Your normal use case is whatever it is, a disk pops, and then all of a sudden you're saying, right, we're going to read every block of every disk now to rebuild this, which is why people want extra redundancy, why they want RAID 6. If another disk fails while you're rebuilding a disk that's been lost in RAID 5, you're gone. And the same thing with RAID 6. And as disks get bigger and bigger and bigger, you want more and more redundancy. So one example is in Solaris, or rather in more broadly now, under the OpenZFS problem. There was RAID Z, which is equivalent to RAID 5, RAID Z2 equivalent to RAID 6, and they added actually RAID Z3. So that was originally how I found out about all this stuff, probably about 10 years ago when, I'll add it to my notes, but Adam Leventhal, I think, wrote a blog about exactly this, how Linux does it in RAID 6, and pointed me at all these papers a little while ago. Does that answer your question? So we're saying some number of normal data, some number of parity, and it's typically 1 or 2 parity for n data blocks, and n's typically less than 8 in a realistic system. And then if you've got more disks than that 8 or 10 that I'm suggesting there, then you have to do something like I'm proposing now. You wouldn't have a 27 wide RAID 5 stripe, because as soon as you lose a disk, you have to read from all the others. And that's problematic. That's in part what Erasure codes help with later. Does that answer your question? And thanks so much for it. I feel like I'm not just talking to avoid now.
Yeah. Thanks so much. Yeah, I see that there are quite a lot of trade-offs. I was also thinking that this kind of extends beyond disks, right, to like cloud environments, like
definitely getting there. Let me speed up. We'll get there. I'm mindful of time now. So we can layer these things. So RAID 0 across RAID 1 across RAID 0. You can see there we're writing A1 to those 2 disks, A2 to those 2 disks. So we got RAID 1 atop RAID 0. Not so used. More commonly, you'll see hardware RAID providers will provide RAID 10, which is RAID 1 combined with RAID 0 over them. So RAID 0, if you remember, was performance enhancing, but failure domain increasing, or probability of failure increasing. Here we get a little bit of a mix of both, where we can definitely survive 1 failure here. We've got a chance of surviving 2 failures, right? So the number of failures we can tolerate in this case, if we lose a disk from each RAID 1 array, we're golden, aren't we? We can use the other one. So that our durability here isn't just we can survive 2 disks failing, or we can survive 1 disk failing. It's somewhere in between, and that's going to become important later. You can layer RAID 5. You can stripe across RAID 5 arrays. This is called RAID 50 typically. And this would be, and again, you're trading off storage efficiency. How many drives have you given up to parity, to performance. You don't want to read from every drive in order to do it. So this is an example where, do you see, we could survive potentially 1, 2, 3 drives failing here, as long as they weren't all in the same subarray. You can survive 1 drive failing in any RAID 5 array. Similarly with RAID 60, you can survive 2. You could survive actually up to 4 drives failing here. I hope you can see in either of the RAID 6 arrays we can tolerate 2. But then if we lose more than 2 in a subarray in one of the RAID 6 arrays, we actually lose data. We can't reconstruct that block device that we're emulating, right? This is an interface. We're saying we're taking some number of block devices and presenting a block device, perhaps to a file system. If a segment of your block device disappears, your file system doesn't know what to do. So that's like the interface we're honoring. And then there's crazy ones. This is RAID 100, and even though this existed till I checked the Wikipedia article this week. So RAID 1 layered on RAID 0, striped on RAID 0. But you can kind of see there, what can we survive? Well, any of those RAID 1 arrays, we can lose 1 device from, right? So we could survive up to 4 devices, but we've only got a probabilistic guarantee of surviving more than 2. So I hope that's clear. So now, to the chap who just spoke point, we've got Windows as your storage, or S3 or something. We've got blobs of files or blobs of data that we're storing for people. And we can do a similar trick. We can say, well, we can carve the data up, we can generate parity blocks, and we can disperse them everywhere. The typical dispersal strategy or the redundancy strategy for lots of these things, like Hadoop and I forget which Google paper it is that informed the idea, but it was like, we put 3 copies of everything everywhere. Now that can make sense, but you're writing everything 3 times in that case. Do you remember in the RAID 5 case where we were like 75% efficient? In the case we had 4 drives, and 3 of them were used for data, 1 of them was used for parity. We were getting 75% of all the storage we use. In the case where you do everything 3 times, you're potentially only getting 1/3 of the storage that you've got. So an erasure coding strategy is good, but you have to do work to recover it potentially, or you have to fetch it from multiple places. So that's potentially problematic. So it's a trade-off between storage efficiency and performance. And for something like Hadoop, thanks to Andrey for the I couldn't remember if it was Bigtable or GFS. So thank you. So yeah, you're trading off storage for storage efficiency for performance. But the thing is, if you're doing something like Hadoop and you're doing compute on the data, the lesson of Hadoop was bring in the or MapReduce more broadly, bring in the compute to the data. If you have to go to other machines to reassemble the data you're interested in, that's not so good. But then if you can do it on a part of the data, like you don't need to reassemble the whole file, then maybe you can put up with the fact that it's spread over multiple machines. So I like this paper. This is a new paper for me. This is an offshoot. I was talking with my partner recently about the way one reads papers, because it's more like a tree. Literally every time there's a little call out, that could be another paper, right? I haven't completely explored the tree of the paper I'm talking about, and there's loads of good ones. So this one was new to me in the last fortnight or so. So the erasure coding in Windows Azure storage, I didn't know actually the way Windows storage works. I've not really used Azure much. They write a binary log in triple that accounts for everything. So it's the volume store, it's the blob store, and it's also a database. But then after they've written it out in triple, they say they erasure code the blocks that are left. So you're writing out first in triple, then erasure code in what's left. But that can be an asynchronous task. You can erasure code it offline, delete the existing 3, and then have your record, your archive is then space efficient. But you're in the production case, you're just writing simultaneously to 3 binary logs. So I thought that was interesting about this paper. That was certainly news to me. But they've got this idea of so-called local reconstruction codes. And I love this paper because this picture is exactly like the RAID picture we've seen so far, except it says, hey, for X0, X1, and X2, we're going to write a simple parity. let's assume it's XOR for now. It actually isn't, or actually isn't always, or necessarily, let's say. So we say those 3 disks have got some parity. So if any of those disks fails, if one of those disks fails, we can look at that parity. And the same is true for Y0, Y1, and Y2. So this is the local parity idea. That's why it's called local reconstruction codes. We've got 6 bits of data. We've written 4 bits of parity, but we only need, in the case we lose 1 drive, we only need to look at 2 other drives. We've saved our, in the simple case where we've lost 1 piece of data, we've saved what we need to look at. And that's the enhancement. When the data's over away on another machine, you have to minimize having to reach out somewhere else. So let's assume, and because it would work, it wouldn't be as efficient as what they've actually got potentially though. So if you look, we say x1, x0, x1, x2, and then px, y1, I don't know why I'm counting at 1 when it's obviously 0. Y0, Y1, Y2 with the parity Y. And then these extra global parities, they could be XOR and ReedSolomon as per RAID 6, right? You could imagine this being RAID 6 with some local parity information. Local parity being XOR is fine. They don't conflict because it's 3 disks, not the 6. It's not the redundant information where we couldn't solve before. It's actually a different case. So we could do it like that. So what's really interesting though, the particular code they generate is even more efficient than that. We can definitely survive 2 failures because of the global parities. But how many of the 3 failures can we account for? Or how many of the 4 failures can we account for? And what's nice about this is they account using a clever coding scheme. And again, I'm going to punt on the explanation. It means, once again, a good matrix was chosen. They can account for 86% of all of the possible 4 failures. So if you look, if we break 2, we can go to the global disks. If we break 1, we can go to the local disks. That's fine. If we use the schemes we've understood so far, like RAID 5 and RAID 6, we can do that. They've got a clever encoding that allows them to actually to solve nearly all of the 4 failures of the 6 data drives. So 86% of the 4 failures are dealt with. And what's really nice is they compare it with ReedSolomon codes. So ReedSolomon says we've got 10 data, 4 parity in this case, or we've got 6 data, 3 parity. And I hope you can see the arrow on my screen. So ReedSolomon is here in this space. How much storage overhead are we paying? And what's our read penalty when we have to recover? And you see that this is the space of possible configurations in their scheme, but being down here is good because we're not paying a reconstruction cost. Being over here to the left is good because we're not paying a storage overhead. So they quite correctly say, well, let's look at the lower bound. Nobody would choose any of the things over here. They're dominated. Do you understand? There's strictly greater configurations we can choose, and if we choose them, we get this line here. So we're not interested in any of these configurations, right? We're choosing this, and these are particular parameters to the code. So 622 are the choices you make, and 6 data, 2 local, 2 global is the 622. So that particular I forgot what LRC means. That particular local reconstruction code. I didn't have to admit that, did I? So that particular local reconstruction code is information theoretically maximum. So there's another interesting paper that you can take in. It's like they're actually in some optimal space here, because if you lose both drives of a RAID 1 system, you can't. No clever scheme is gonna stop you dealing with the fact that all your data is gone. So you've got this comparison here, and what's interesting compared to the SEF, compared to the shingled, the SHEC code that we'll talk about later, because LRC is also in SEF. SEF actually has 3 options for erasure coding. So yeah, this is the lower bound here, the only ones we're interested in from this side. But here's the ReedSolomon codes. So you can see actually they're strictly better on this graph. The reconstruction cost is lower. The storage overhead is lower as well. So this is in some sense like they're showing by this graph, like we're better than ReedSolomon codes. And there's a little note like in the RAID 6 paper about Galois fields and doing arithmetic and how it's not very well tied to modern CPU architecture, but here's some tricks, right? So again, I'm going to punt on that description. So another paper, which is listed in the prereqs of the SHEC paper I'm going to get to now, might make sense to pause now. I feel like I'm excited. I should probably calm down. This is I love this stuff.
Any questions coming from the audience?
Yeah, this is great, Tommy. I'm lapping it up. Did you you're kind of coming from quite a mathematical background, and I haven't done much maths for very many years, but when I was studying engineering, they were telling us about Hamming codes, and my memory of them is that the math was quite straightforward on them. Did you know how they compare to ReedSolomon style codes and Galois Field?
Not off the top of my head. So my favorite module in uni was coding in cryptography, and it was around the time when what became AES was for encryption was out. But we actually went through and studied all of the different candidates for what became AES. So at one point I knew this stuff super deeply. Now I struggle to remember bits, whatever. So I'm probably 15 years now off giving you a correct and succinct answer there. But this is not it's not super hard given other mathematics you probably know. I've punted an explanation now, but that paper, the mathematics of RAID 6, is probably enough to get started. If you think about it as solving equations in a world where there's a weird arithmetic on bytes, you're not that far off. And you can do it, but not super efficiently with a lookup table. So you can literally, they actually use they use the equivalent of logarithms to do the multiplication. So then everything becomes about XOR is the trick. But yeah, there's kind of two dimensions you can go into. You could actually, if you think about it, brute force them and saying, I have to satisfy these three equations, generate every byte sequence and find the only one that matches. So you could actually be really naive in terms of recovering data. And I was tempted to do it in Python or JavaScript before this talk, to be honest, and say, look, I haven't solved anything. I just trial and error and get the results out. But I haven't had a chance. I've been too busy with my new job. But a good question, I think. Sorry for waffling in the answer.
It's super weird when you start doing those experiments because you run up against the reality of information theoretical limits, because start to wonder, like, isn't all my data just in the lookup table somehow? Just need to find it.
Well, all you're doing is speeding up the arithmetic at that point. So it's not your data. The interesting thing from the RAID 6 paper is even then, even 10 years ago, lookup tables being inherently sequential, you weren't taking advantage of parallelism in the CPU. The CPUs have got faster now and more parallel now. Sorry, not faster. CPUs are doing more and more clever stuff to make up for the fact they haven't got faster. But again, I'm not going to pretend to know that quite well. I know the mathematics better than the high performance computing side of this thread. I can't see you
moving in cryptography to going for more like lookup table based algorithms because they weren't parallelizable on CPU.
Yeah, so one thing that was a gap when I was quite into like breaking encryption, like rainbow tables were a thing when I did it really well, and the cryptographer laughed at me within the last few years because I was like, oh, like rainbow tables, I remember them. He's like, mate, we just use GPUs now or whatever. Like there's no like the world has kind of shifted on a little bit since. I'm gonna move on because the next two papers are super interesting as well. This is a slightly different take on it. But thanks for that was Andy, I think, right? I think I can recognize your voice.
Yeah, that's right.
So in here, this paper actually says we're going to do an encoding, and it's similar. It's LRC codes again, but they actually say, well, we do the local parity block. We have all the ReedSolomon parity blocks, so there's 4 of them. We can recover from 4 of the 10 disks failing by hitting the global parities. We've also got local parities, which we then can have an implied parity. So implied means kind of derivable from other things we know. It means only by looking at S1, S2 if we lose a parity block, we only need to look at S1, S2, and the other 3 parity blocks in order to reconstruct the parity block. Does that make sense? So we've got the encoding scheme is so clever, to be a little bit blasé about it. They chose a good matrix such that they can, if one parity goes, they don't need to recompute it from the data. They can recompute it from the local parities. So they're saying, like, let's take advantage of as much information as we can. Let's get everything working together. Let's select our local parity and select our global parities such that if we lose one of the global parities, we can reconstruct it by looking at the local parities. So I think that was clear, and I'm certainly excited. It's really strange to just talk into a board, so excuse me if I get freaked out every now and again. So they've got them. So the 4 are just straight up ReedSolomon, but the local parity and this implied parity are chosen such that, and it says the main theoretical challenge, and again, like the main theoretical challenge is to choose the coefficient Ci, as in the elements of the matrix, to maximize the fault tolerance. So the paper says, it turns out the coefficients can be selected, blah, blah, blah. And it's like, here is how we select the matrix to make the equations you need to solve. And what I think is really nice is that at the end of this paper, which is great actually, in the appendix, the third appendix, actually an explicit LRC using ReedSolomon parities. There's a typo that's passed like N reviewers, because everybody's kind of like, all right, okay, folks, you made a good matrix, well done. There's actually quite an obvious typo in the final bit. So, but it actually doesn't matter to your understanding. Your understanding is it's a really great idea to have local parity. So we don't need to be like able to or willing to go and churn through all of the mathematics. This is a good layout for parity blocks, it turns out. If I lose x1, x2, x3, x4, or x5, I just look at S1 and I can recover, right? If I lose 2 of them, I need to go to the global parity. If I lose 3 of them, I need to go to the global parity. And of those 10, I can afford to lose 4 just based on the global parities, plus some extra from the local parities as well, because they're working in concert. That's brilliant. That's brilliant because it's efficient in terms of your recovery, and it's optimal in terms of your space use. But more importantly, you've got more choices when you're selecting the trade-off. So I hope without trying to off the cuff explain the mathematics I plan to punt, I hope people can understand this idea. So now the paper we promised today, and something like on time. So thanks for your indulgence thus far. So where we are now is you can take some number of blocks of data on a RAID system. They're blocks in a block device and assembled to another block device, fed to a file system. For a distributed storage system, it's carving up your files and writing some extra information without having to make 2 or 3 copies of your file. Make some extra information that lets you recover the file. If you ever did any news group stuff, like downloading files from the internet, whatever, PAR files are like this. PAR files are saying, if you've got the PAR file, but you're missing one of the parts, you can recover the part. So I'm going to move on unless there's any interjections. Cool. So this is shingled Erasure code, which is one of my favorites. The paper's short and sweet, but like I was describing, obviously all the references, if you track them all down, there's still dozens of references I haven't tracked down. But SHEC says designed for efficient recovery in the event of multiple disk failures with space efficiency and durability adjustable according to user requirements. It's an Erasure code with local parity groups. So what they're saying is we've learned the lesson from these people. And the 2 other papers I've mentioned were called out in this paper. So they're saying, well, given that these folks have done good work, can we make it slightly better? And what I really like about the RAID ideas and the local parity idea is it's comprehensible, right? Even if you don't understand the Galois fields and the particular equations, just the locality property of I only need to look at these 2 disks to do my recovery is nice, right? It's simple. It's like an aha moment. The aha moment, if you haven't read this paper now, is, oh, well, what if everything was sort of kind of local? Like, there is no global parity over there that we reach out to, but we interleave, we shingle the parity. And this picture's not very good compared to the other pictures we saw before, because P1 in this picture looks bigger than D1, D2, D3, D4, D5. That's not the case. Parity is the same size, and you should think about it. I don't know if they use this terminology, but you should think about it as like covering. So P1 covers disks 1 to 5. P2 covers disks 3 to 7. Yeah? P3 covers disks 5 to 9. So you've got this overlaid parity where in order to do a recovery, you have to choose which parity you're going to use, but there's an algorithm to do that. And then you say, well, given that, I can recover. So if we have some failures, I believe this is a failure that cannot be recovered. So this is a 4 failure on SHEC 1065. And it says if disk 1 goes and parity 1 goes and parity 5 goes and parity 6 goes, that data's gone. And that's comprehensible, right? Disk 1 is covered here by P1, P5, and P6. So if you kill not disk 1, data block 1, if you kill data block 1 and all of the parities that refer to it, then it's gone. That's a simple idea, right? And there's a bit in the paper where they say, hey, we chose a good matrix. But then here is what ReedSolomon looks like in their picture. So for the 6 disks, we've protected them with 4 parities. So ReedSolomon 6-4, 6 data, 4 parity. We've got 10 disks. Oh, excuse me. I was thinking the disk case. That's not that. Ignore that. For every 10 blocks of data, I need to be more precise. If we've got 6 blocks of data, we're protecting them with 4 blocks of parity, right? In the ReedSolomon case. Sorry, I fluffed that. We've got 6 blocks of data, and then we have to write 4 parities. 6 blocks of data, 4 parities. SHEC 643 looks like this. For those 3 blocks of data, D1, D2, D3, we write 1 parity. So we have to carve it up, but you see that the offsets are different. We've got P1 there is offset by 1 to P2, but then it's offset by 2 to P3. So you've got an extra, the interleaving can be more flexible. We can say sometimes we skip 1 data, sometimes we skip 2, and we've just got some coverage for the data blocks that we're interested in. So how does SHEC 643 compare to the ReedSolomon codes? And what's great about these papers again is, without talking in great detail about the mathematics, we've got a graph that draws out exactly why this shingled approach is better. We've got the Zorbas paper. I love the title of the Facebook paper about elephants, XOR in elephants or whatever. But Zorbas is that paper. If you've got 1 local failure, then you're here. Your recovery overhead is low. But as soon as you reach to global, you're here. If you're in the ReedSolomon case, you've always got to read everything. You're always in this worst case. Yeah? In the case of the Zorbas, you're very efficient until you go to global. I hope you can see the pointing on the slide. But in the LRC case from the Microsoft paper, you're golden again until you go up here. But look, the scheme they're proposing says, well, if 2 fail, you're here. If 3 fail, you're here. So you gradually approach this worst case, and that's really, really nice. So once again, like, this is the thing that should be shouted about the paper, which I am quite excited. Excuse me. So that's the end of the actual paper I wanted to talk about. So before I go on to talk about the death of the block device abstraction, any questions there? I hope that was clear and exciting. I'm excited even though I'm talking into a void. I can just see Renzo's face.
I have a question.
Yeah, there are a couple of questions also on the chat.
Oh, cool.
Go ahead, Kush.
Oh, I'm sorry.
I have a comment and then a load of questions. I'll have 2 questions, but the comment that I was just going to say is your story about here's a magic table. made me think of ZFS released a magic table, which was given on one axis your IOPS and the other axis your redundancy. Pick your configuration based on your tolerances. And then they had to release, this is like over 10 years ago now, but they had to release an updated table because they only tested some of those cases in their matrix that they released.
Yeah.
And they went back and worked out, no, you can't just extrapolate the data based on what they tested. The maths is actually slightly different. My question then was going to be, at what point does this become turtles all the way down? Like there's a point where you've kind of described this kind of RAID 0, RAID 0 plus 1 or 10 or whatever. You've got these parity blocks. At what point do you, at what level of storage size and capacity do you then have to worry about global versus local nested parity blocks? Because there must
so I think it's not a failing of any of these papers. It's a failing of my exposition. You're paying a tax. So for 6 blocks of data, you need 4 blocks of parity, right? So, but these codes are in some information theoretical sense optimal. So there isn't especially when we took the limit in the LRC case, because some of them are dominated, right? So I'm trying to talk while also looking at the chat. I'll talk and then I'll address the questions in the chat in 1 second. So I'm sorry if I didn't stress it, but there's kind of optimality results that say everything that you can plausibly recover given the amount of penalty you were prepared to pay or given what you've paid. So they're kind of optimal in that sense. Does that make sense? You could survive, have a greater durability, let's say, by having more parity, and we would use those parity blocks that you gave us. We would use them optimally.
Yeah, cool. That makes sense. Thanks.
I'll if you look in the paper, they call it out at one point. I remember it's like note 12 on the Microsoft paper, so I can put it in the chat quite soon, I think. Because that's the thread I haven't fully explored, right? Exactly what that information theoretical property, which is novel work, fairly recently, I haven't explored yet. I should also mention, actually, I've started working at a place called Protocol Labs, and a colleague of mine now has got a paper about rateless erasure codings. I haven't had a chance to check in as well. So there's a whole, these are rated in the terms of every 6 data, you've got 4 parity, 6 data, 4 parity. There's a whole field of things called rateless codes. And I had seen Tornado and Raptor encodings. Raptor was patent encumbered, I remember. But my new colleague actually has another earlier paper that's equivalent to the Raptor paper. So there's a whole other class of rateless encodings for erasure coding, which might be better in the peer-to-peer case. We're looking at you, one entity, writing some parity information out to efficiently recover blocks of data. I'll try and address the questions. I wonder if it makes sense if I finish the Prezzo, and then we pile into a less formal chat. So it's not me talking to you, but rather us talking. And I can
actually in the chat, we got a couple of comments, so we can probably take them later on. It's not just cool questions.
Thanks for the assistance, Renzo. So the next thing is then, like, this, to me, block abstraction's been super fruitful. So one of my favorite things in sort of the interface between DevOps or Dev and Ops, where I've spent the last few years, is like, if you know about these abstractions, and it's great, like if somebody gives you an iSCSI device, but it's really slow, so that's a way of doing block storage over the network. And if you're read skewed, there's a whole bunch of things in the Linux kernel that will say, well, I'll fake a block device and I'll use the fast storage I've got locally. And if you read a block that you haven't rewritten, I'll return it from local storage. So that's called, there's a whole framework in the Linux kernel called the device mapper, which takes block devices and assembles block devices. There's two different RAID subsystems inside the Linux kernel as well. There's DM RAID and MD RAID. But so that's just a way of combining block devices. There's the whole field of logical volume management as well, which is so let's say your block devices slowly expanded, it's thinly provisioned. That's also a possibility. This abstraction permits a lot of things. The reason I mention that is, like, you can layer file system abstractions and say, well, we'll back to S3, but if we only write some small fraction of what we want, whenever we read, we can read locally, if we can promise that nobody else is changing the data from underneath us. Now, a block interface is not naturally shared writable between multiple sources. File system makes a slightly different promise, but those layers of abstraction are really nice. And I kind of like, there's an interesting analogy between that and just the mathematical abstractions, right? If something's a field, then they can be elements in a matrix, and you can solve equations in them, and that's just how it works. Like, so that's really fruitful. So I'll do, I think, 3 more slides and 1 more paper, and then we'll pile into a less formal chit chat. So this block device abstraction, which I love, might be dying because SSDs get faster. If you write the same block repeatedly in an SSD, it'll wear out. So what the SSD will do is move the block. You have so-called wear leveling. So the SSD accepts block as an interface, but underneath it will move around the blocks, because you write into one block all the time. It's not a good idea for the SSD, but they have to honor that interface because file systems expect it. There's 2 different pushes towards not accepting block, the normal block interface. One is in the sort of faster storage space, is this SSD example, which has existed for a while. There's this thing called shingled disks as well, which is a nice resonance with the shingled Erasure codings, which allow you to get higher densities on hard drives, but they require you to write linearly to them. So we've got a push, I've got the link there from Western Digital. Linear writes only to the device, but then either denser or faster storage is the promise. And there's the Ceph people towards the tail end of last year, one of my favorite papers of last year, did a thing about an exploration of using file systems as the target storage for distributed file systems, using local file systems as a target for distributed file systems, and why that's not a good idea. And their answer was to write something that directly consumes storage devices. So the no file system, we're not creating files in a file system and serving them up in our distributed system. We're directly consuming the storage device. If we do that, we play nicely with SSDs, we play nicely with new shingled hard drives, and they do a nice thing, and the paper's lovely. And I think the morning paper, Adrian Coiler or whatever his name is, has done a nice description of it. So that's another great paper. And they do just enough of a file system, which is the so-called BlueFS there, in order to implement RocksDB. So a file system is metadata from, these are your files and folders, and these are the things that get written to the block device. They're saying, well, we'll write directly to the block device, and we just want a little bit of information, a little bit of metadata around where they are, what the offsets are, or whatever. So that's super, super interesting for me, because it felt like a good idea. Both Gluster and Ceph did it for a while. Ceph is a distributed storage system now owned by Red Hat. Gluster and Ceph both did the same thing, which is punt storage to the local file system because they're tried and tested. And now this kind of unraveling of that assumption and saying, hey, maybe we want to just directly consume block devices, or excuse me, directly consume disks in order to permit this linear access as described in this zone storage initiative from Western Digital. Western Digital also got into trouble for shingling disks but not telling people about it. So if you play nice with shingled disks, they're good. That's completely separate to the shingled encodings I spoke about. So I'm not being very clear now. I shouldn't go off piste. So yeah, any questions?